In this chapter, I'm going to show you how to use a number of important Docker commands. But before we get started, I need to point out that you won't use these Docker commands to run containers in a Kubernetes cluster. Kubernetes has its own commands for that. That said, Docker commands are still useful. You'll use them when you're prototyping and testing containers before putting them in your cluster. So, let's dive right in.
The first thing that we need to do is install Docker. Follow the instructions that apply to your OS at docker.com/community-edition. Then start it up. Now that you've installed and started Docker, let's run a container. Open up the terminal and execute the following command. We just ran the printbig container. Here's what happened under the hood. First, we instructed the Docker client to create a container from the printbig image. The client then forwarded the docker run command to the Docker daemon. The daemon checked the local image cache, but couldn't find the printbig image. So the daemon pulled the image down from Docker Hub, the daemon's default image registry. Once the image was fully downloaded, the daemon used it to create a container. Then it started that container. Next, the daemon sent the output from the container to the Docker client, which then forwarded it to the terminal for us to see. Finally, the Hello World application in the container terminated. This caused the container to stop. That's it. Now we're ready to start looking in depth at some important Docker commands. Let's get to it. The create command makes a new container, but doesn't start the container. It just creates the writable container layer and prints out the container ID. The optional command and arguments are what get executed inside of the container once it starts up. Let me show you a couple of examples. First, let's create a new container based off of the BusyBox Linux image. Okay, Docker just pulled down the BusyBox image from Docker Hub. Now, the cool thing about the BusyBox image is that it's incredibly small. Even though it's a functional Linux OS, its size is only a few megabytes because almost all utilities and programs have been completely stripped out. That makes it very quick to download. I often end up using BusyBox as the parent image for a lot of custom Docker images that I create. Then I just install the one or two utilities that I need as the situation requires. Now let's list all containers on my machine. This is the container we just created. There are two ways to determine this. First, it's the most recently created container. Second, these 12 or so container ID characters match the first 12 or so characters of the container ID, which was spat out by the create command. Notice that the container also has a name. When you don't supply a name, Docker automatically assigns the container a pseudo-random name based on a combination of a random adjective plus the name of a famous scientist. When you need to refer to a container, such as in a Docker command, you can use the container's name or its container ID. It's up to you. Note that you don't need to supply the whole ID, just a unique prefix, i.e., enough characters to uniquely identify it on your computer. Let's create a new BusyBox container and give it the name Lizzie. The start command tells Docker to start running a container which is currently stopped. As an example, let's start by creating a new container from the clock image. Why don't we name it Clocky? Now let's start running the container. Unfortunately, we don't see any output from the container. This is because the start command does not attach to the container's standard out and standard error streams by default. As you can see, the container is running, but we don't see any output because it's running in the background. Let's start the container again, but this time add the attach flag. This attaches the terminal to the container's standard out and standard error streams. The result is a simple digital clock right on the command line. To stop the container while you're attached to its standard out and standard error streams, just press Ctrl-C. The run command is basically just the combination of the create command and the start command. You pass the run command an image, and it then creates and starts running a new container from that image. Let's go over a few examples. At the beginning of this chapter, I showed you how to use the run command to run the printbig container. By default, this container prints out hello world. But we can change the output by passing a new message as an argument to the container. The Star Wars argument gets passed to the container's default process. This container's default process is a Python script which prints out some big-ass ski text. You may have noticed that, unlike the start command, the run command starts up a container and attaches its output streams to the terminal. Oftentimes, that's what we want, but sometimes we want the container to run in the background. To do this, just add the detached flag. For example, the container ran, printed out the message, and then exited. On a slightly different note, keep in mind that you always need to put the command line flags before the image name. When you run a container, its standard end stream isn't open by default. Therefore, the containerized process cannot receive input. For example, let's say that you want to pipe a string to the sort command in a Ubuntu container. Unfortunately, this won't work because the container's standard input stream is closed. To open the container's input stream, just add the interactive flag. I find that I often need direct terminal access to a container. In other words, I often want to be able to interact with the container as if I'm SSH'd in. To do this, you need to include the interactive flag and the TTY flag. The interactive flag keeps the container's standard input stream open. The TTY flag allocates a pseudo terminal. For instance, here's how you run a new Alpine container and get direct terminal access to it. We can see that we have a terminal in the container because the command prompt changed. And when we list the current directory's contents, we see the contents of the container's root directory. In case you're wondering what Alpine is, it's just another super lightweight OS image like BusyBox. When we want to stop the container and exit out of it, you can either press Ctrl-D or enter exit. So you might be wondering what happens if we do not include the TTY flag. Well, let's run a little experiment and find out. Notice that there's no command prompt. However, when I enter the ls command, we do get the contents of the container's current working directory. In other words, the container is receiving input, but there's no terminal. As a consequence, we don't get benefits like environment variable expansion and all these other cool things that the terminal does for you. That's why we need to include the TTY flag. When you run a container in interactive mode with a pseudo terminal, sometimes you want to detach from the container without shutting the container down. All you need to do is type Ctrl-P, Ctrl-Q, and Docker puts your container in the background. You may have noticed that whenever a container stops, it's still on your system. For example, as you can see, the container's stopped, but it hasn't been deleted. If we add the RM flag, the container will automatically be deleted after it stops. Check it out. This is pretty handy when you want to run something in the container without leaving a mess behind when you're done. Some applications, like servers and databases, receive data via a network port allocated to that application. Send data to that port and the application will receive it. For instance, let's say that you run an Nginx web server on your computer. You can make requests to the server by visiting localhost:80 in your browser. Things get a little bit more complicated for containerized applications. You see, a Docker container has its own set of ports which are completely separate from the host computer's ports. When you make a request to a port, such as port 80, that request is directed to the host computer's port 80, not the container's port 80. What we need to do is map the container port to a host port. Then when we send data to the host port, it will be forwarded to the containerized application listening on the target container port. You can map a host port to a container port using the run command's publish or -p flag. Here's the command format. The argument to the publish flag is whichever host port that you want to use, a colon, and then the container port that you want to map to the host port. Let me show you an example. Here's how you run the Nginx server container so that messages sent to the host's port 3000 will get forwarded to the server container's port 80. This is a really helpful technique when you're prototyping and want to test out a containerized application. As you can see, we're able to make requests to the Nginx server on the container. One thing to note is that the publish flag binds TCP ports. If you want to bind UDP ports, then tack on a /UDP at the end, like this. Okay, we're done with the important bits of the run command. Next up, the stop command. You can use the stop command to stop one or more running containers. For example, let's open up a new terminal and use the stop command to stop the Nginx container that we started in the previous example. You can use its name or a unique prefix of the container ID. In this case, the first 3 characters uniquely identify the Nginx container. Here's how it works. When you run the stop command, Docker sends the terminate signal, aka sigterm, to the container to stop it. The container then forwards the signal on to PID1, the primary application running in the container. The containerized process with PID1 then has the opportunity to gracefully shut down. When all processes have stopped running, and there's usually only one in a container, the container itself stops. If the container hasn't stopped after a grace period, which defaults to 10 seconds, Docker will send the kill signal. This kills the containerized process immediately with no cleanup.
When you're in a murderous mood, the kill command has you covered. By default, the kill command sends the Linux kill signal to the target container. So, I'm going to use a container called printSignals to demonstrate the kill command. The container runs this Python script, which traps Linux signals, with a few exceptions, and prints them out for us to see. The first thing that I'm going to do is demonstrate how you can use the kill command to send any signal to a container. So let's run the printSignals container and give it the name signal sniffer. Then why don't we send the interrupt signal. If you don't explicitly specify the signal that you want to send, the kill command sends the kill signal. See? This kills the container immediately, giving it no chance to clean up. For a list of Linux signals that you can use, check out the man pages. Let's talk about the difference between PS and PS-A. PS lists all running containers, whereas PS-A lists all containers, running and stopped. For example, let's start by running a new Nginx container. After I stop the container, it no longer shows up. However, by adding the all or -a flag, we can now see all containers, including the one we just stopped. Docker automatically caches the images that you build or pull down from an image registry. When you want to see a list of the cached images, just run the docker images command. Over time, as you work, stop containers pile up. See? In this video, I'm going to show you a few different ways to delete unwanted containers to free up resources. Here's how you delete one container from your Docker image cache. To delete more than one container at once, just list them as additional arguments, e.g. You can include the force flag to delete containers that are currently running. But be aware that the force flag sends the target container the kill signal, meaning that the container won't do any cleanup. If you want to delete all stopped containers, but no running containers, then all you have to do is run the container prune command.
The RMI command is used to delete an image from your computer. For example, let's delete the Alpine image. Keep in mind that an image is uniquely identified by its repository name plus image tag. So we pass the RMI command the repo name Alpine, a colon, and then the tag latest. Of course, we could have also used the image ID. In previous lessons, I showed you how to run a container in the background using detached mode. I also showed you how to detach from an interactive container using Control-P, Control-Q. The question is, how do you reattach to a background container? You use the attach command, of course. You see, the attach command gets its name from the fact that it can attach streams like standard out and standard error to the target container. For example, let's start by creating an Alpine container called Secret Project. Next, we're going to detach from it. Now we're going to reattach to Secret Project like this. I'm going to exit out of this container so that we can look at a second example. Watch what happens when we create a new container called Cover Story with the interactive flag and the detached flag. When we reattach to Cover Story, we can see that standard in is opened, but there's no terminal and therefore no shell. This isn't really surprising since we didn't allocate a pseudo-terminal when we first ran the container. My point is simply that the attach command does not automatically give you terminal access to a container. If that's what you want, then check out the next video on the exec command. Let's talk about the exec command. Its purpose is to execute a Linux command that you specify in an already running container. Here's the scenario. We're going to run an Nginx web server container in the background. Let's use the publish flag to map port 80 on the container to port 80 on the host computer. Lastly, we're going to name the server myblog. Now let's say that we need to change the contents of the homepage. How do we do that? Well, your first answer might be to use the attach command, but all that will do is attach the container output and error streams to your terminal. We won't have standard in or shell access to the container. What we need to do is use the exec command. Let me demonstrate. Just pass it the I and T flags like we've done with the run command, and then the name of the container or the container ID, and then the command that we want to execute on the container, in this case the bash shell. Now we have terminal access. To change the contents of the homepage, we need to go to the user/share/nginx/html directory, and then update the contents of the index.html file. Now let's check out our handiwork.
The docker copy command can be used to copy files between a container and the host computer. I'm going to start by showing you an example of how you can copy a file from the host to a container. We're going to start out by running a new BusyBox container called copycat. Now we're going to create a file called message and copy it to the temp directory of the copycat container. You list the copy command, the file to copy, the target container, a colon, then the path to copy to. Let's go back to the first terminal and verify that message was copied over to the container successfully. Now let's create a new file called response in the container. Next, we're going to copy that file from the container to the current directory on the host. A Docker container will automatically log all output sent to its standard error and standard out streams. You can then view these logs using the logs command. Let me show you an example. Let's create an Nginx container again. It's going to run in detach mode, and we're going to map port 80 on the host to port 80 on the container. Next, let's visit localhost in the browser. This will cause a few lines to get written to the web server's access logs. The Nginx access logs live in var log nginx. Let me show you. Using the exec command, we're going to ls-l the default log directory. Because this server lives in a container, the log files are actually linked to the standard out and standard error streams. This way, the container itself logs these messages.
Now, here's how you get the log output. You just run the logs command and pass it the target container's name or part of its container ID. By default, each container logs to a JSON file using a JSON log driver, an internal Docker plugin for saving container logs. I only bring this up to let you know that you can configure Docker to use different log drivers, such as FluentD, syslog, and even Splunk. The details are beyond the scope of this small course, but if you're interested in the subject, I suggest that you check out the Docker documentation. By this point, you've learned a number of different useful Docker commands, but we've yet to go over how to create a Docker image. Let's fix that. One way to create an image is to run a container, make some changes to that container, and then commit the changes to create a new Docker image. For example, I'm going to run an Alpine Linux container and give it the name curly. Since Alpine is such a stripped down operating system, it doesn't have utilities like curl. That's okay because we can install curl. Next, I'm going to exit out of the container. The output from ps-a proves that the container still exists. All we need to do to create a new image from this container is use the commit command. This command takes the name of the target container and the name that we want for the new image repository, in this case, Alpine curl. After the colon, we give the image the latest tag. But that's arbitrary. We could have given it any tag name. And there's the image that we just created. At this point, I feel that I need to give you a brief explanation of what the difference is between an image registry and a repository. Earlier in this course, I told you that an image registry, such as Docker Hub, stores container images. That's true-ish. But to be more precise, an image registry stores one or more image repositories. Each repository stores all of the versions of a particular image. Each image version corresponds to an image tag. There's a bit more that needs to be said about images and tags, but we'll get into that in a minute. For now, consider this. Creating images by manually modifying containers and committing those changes is not a very reliable tactic. Don't get me wrong, the commit command is helpful in a pinch, but being a manual process, it's hard to reliably rebuild an image. After all, humans make mistakes. What we need is some sort of script for reliably creating Docker images. That's what Docker files are for. And that's why we're going to learn all about Docker files in the next chapter. Thanks for watching.